Okay, we have a great section here, 4.5, integration by substitution. Okay, this section discusses techniques for integrating composite functions. You know, we use chain rule for composite functions. So there are two main methods introduced: pattern recognition and change of variable. One glaring difference in these techniques is that in pattern recognition, the steps are performed mentally. So I'm not really a big fan of the pattern recognition. If you see it, great. I'm really happy for people who can see it. I tend to write everything out just so I don't miss something. But through change of variable, the steps for substitution are written. So the use of substitution in integration is comparable to the use of the chain rule in differentiation. So recall that the derivative with respect to x of f of g of x is f prime of g of x times g prime of x. So it's the derivative of the outside function with the inside function unchanged times the derivative of the inside function. Antidifferentiation of a composite function: let g be a function whose range is an interval I, and let f be a function that is continuous on the interval I if g is differentiable on its domain and f is an antiderivative of f, little f on I. Then the integral of f of g of x times g prime of x dx would be capital F of g of x plus c. Now, here's the u substitution. If u is g of x, then du would be g prime of x. I should have written dx. And the integral of f of u du is f of u plus c. So notice that there are two functions to consider: the outside function and the inside function. G of x is the inside function, so you have your inside function, you have the derivative of the inside function, and f is your outside function. So we're going to try completing this table here by identifying u and du for the integral. So in this one we have integral of x squared times the square root of x cubed plus 1 dx. We can rewrite this as the integral of the square root of x squared plus 1 times x squared dx. And this can become more convenient because then our u would be the part under the radical. We could say u equals, and I think I was supposed to mean x cubed. U is x cubed plus 1, and then our du is this part outside the radical. Our du would be 3x squared dx. Now notice we don't have, in this case, a 3x squared. We just have an x squared dx. So what you could do is then say, okay, I'll divide both sides by 3, and I have 1/3 du equals x squared dx. And that would make this part here that 1/3 du. So the benefit there is you make it fit the pattern. And this is writing all these parts out. This is the substitution format that I'm doing here. Next one, tangent squared x, secant squared x dx. Now, this is a tough one. And in fact, in Calc 2, if you decide to take Calc 2, you'll see that this is this leads into a type of problem where you have a general rule when you have tangents and secants being multiplied. But just remember that secant squared is the derivative of tangent. So that if you treated this as a tangent of x squared, saying that our u is tangent of x, then our du would be the derivative of tangent, which is secant squared x dx, meaning that this part right here is the du. So there are u's here, du is there. So essentially what you have is a u squared type problem. Now how do you do the antiderivative of the u squared? U cubed over 3. Okay, here we go on to the next page here. Find the indefinite integral and check the result by differentiation. Okay, so one, I don't say this is a rule, but it's a good way to start, is make your u the thing under the radical. So if I said u equals 9 minus x squared, du would be, what's this derivative? The derivative of 9 minus x squared is negative 2x, and we put the dx there, so that this portion represents our du. And then this could be rewritten as u, the square root of u du. U is this part under the radical. This other information is your du. And that could be also written as u to the 1/2 du. That becomes u to the 3/2 divided by 3/2. I just added 1 to the power plus some constant c. That's going to be 2/3 u to the 3/2 plus c. And this looks nice and everything, but we really need to go back to what we started with. And we started with u being 9 minus x squared. So this is 2/3 times 9 minus x squared to the 3/2 plus c. Now, we're going to check this, make sure it's correct. So we'll take the derivative with respect to x of 2/3 times 9 minus x squared to the 3/2 plus c. Now we all know the derivative of that constant is going to be 0. That's going to go away. Now we have a chain rule because we have an inside function and an outside function. So the outside function is something to the 3/2. So this is going to be 3/2 times that 2/3 times 9 minus x squared to the 1/2. I subtracted 1 from the power, then times the derivative of what's inside. What's our derivative of 9 minus x squared? Well, the 3's divide out, the 2's divide out there, and what we have is square root of 9 minus x squared times, and this derivative, well, 9's a constant, so the derivative of negative x squared is negative 2x. That's what we have inside our integral. That's it. Kind of fun, huh? And I'll say this is something you will be using throughout the rest of your calculus career. And it's not a bad thing. Once you get it down, it's almost like second nature. Oh, hey, what's my u? What's my du? It's kind of cool. Okay, I'm going to go on to the next one. It says here before we start this, recall that integral of k times f of x dx is k times integral of f of x dx. So for example 3, it says find the indefinite integral and check the result by differentiation. I think it's a lot more fun than doing it the long way with all the summation signs. I agree. Okay. We have something inside of parentheses, so I would say, call that my u. U is the stuff inside the parentheses, the thing being squared. X to the 4th plus 3. So du would be 4x cubed dx. We kind of have that. We don't have the 4 though, so we can divide both sides by 4, and we can say 1/4 du equals x cubed dx. And this could be then written as the integral of u squared times 1/4 du. And then 1/4 can come out. That's 1/4 integral u squared du, which becomes 1/4 of u cubed over 3 plus some constant c. So we have 1/12 of x to the 4th plus 3 cubed plus c. Now we'll check this by differentiation in just a second, but I want to just introduce one other way of considering this problem. What if we had instead the integral of x cubed times x to the 4th plus 3 squared dx? I said instead, nothing's changed yet. But what if we took this one step and said, okay, I'm going to multiply this by 4 over 4. I'm multiplying it by 1. Nothing's changing about the value, but the way it appears is going to change a little bit. Why do I do this? So I can write this as 1/4 integral of 4x cubed times x to the 4th plus 3 squared dx. 1/4 of 4 is 1. We just like what come out. So what we have here is this is the derivative of what's inside. And this is where you'll be doing it in your head all mentally. Not saying you're mental, so you're going to do it in your head though. We have the 1/4 from this part. This is the derivative of what's inside. So we can integrate now, and that'd become x to the 4th plus 3 cubed over 3 plus c, which is your 1/12 times x to the 4th plus 3 plus c. And that's how people do it. A lot of people do like it that way. They like to do it this way, where they're doing more work in their head. Again, I'm not a big fan of that. I like to show my work, and maybe it's because of the teacher in me. I'm used to showing my steps for my students. Honestly, it's been so long since I was a student doing this. I don't remember how I did it back 20 years ago or so. Okay. Now, let's take the derivative and check it out. d dx of 1/12 of x to the 4th plus 3 cubed plus c. That's going to be 1/12 times x to the 4th plus 3 to the 2 power times 3 because of this power, then times the derivative of what's inside, and that's going to be 4x cubed. And we'll end up with, well, the 3 and the 4 divide out with that 12. We have x cubed times x to the 4th plus 3 squared. And that does that for example 3. Now I'm going to go on to the next page, so pause if you need to pause that. Let's talk about the change of variable. Change of variable. If we let u equal g of x, then du equals g prime of x dx, and we get the following. This is kind of what I've been doing already, so this is the formalization of that. F of g of x times g prime of x dx becomes f of u du, which is capital F of u plus c. That's the antiderivative. Okay, so in this one we'll follow the same process. If we say u equals 1 plus x cubed, our du would be 3x squared dx. I have an x squared dx, but I don't have 3 times that, so if I divide both sides by 3, 1/3 du equals x squared dx. So that this part is 1/3 du. And we'd have the integral of 1 over u squared times 1/3 du. And I can pull the 1/3 out. This becomes 1/3 integral u to the negative 2 du, which will be 1/3 times u to the negative 1 over negative 1 plus some constant c. And that's negative 1/3 times 1 over, what was u? 1 plus x cubed plus c. Which is negative 1 over 3x cubed plus 3 plus c. Okay, I'm going to go on to the next one. Feel free to pause that. For example 5, same thing, find the indefinite integral. Now, for this one's kind of interesting, because in this case, if I say u is the part under the radical, like say u equals x plus 2, my du would just be dx, right? Okay, that's cool. I'm good with that. What about this x out front? Well, what if we solve for x? X would equal u minus 2. So this becomes the integral of, ready? X is u minus 2. Square root of u plus, well, x plus 2 would become u, so we have the square root of u. This part is u, so it's the square root of u du. And that's going to be the integral of u times the square root of u minus 2 times the square root of u du. That's u to the 3/2 minus 2u to the 1/2 du. That becomes u to the 5/2 divided by 5/2 minus 2u to the 3/2 divided by 3/2 plus c. that's going to be 2/5 u to the 5/2 minus, well, 4/3 u to the 3/2 plus c. But we're not finished because we have to substitute back to get the x. And that's going to give us 2/5 times x plus 2 to the 5/2 minus 4/3 times x plus 2 to the 3/2 plus c. There we go. That was fun. You can probably tell I get a little excited about these. Okay, we're going to go on to example 6, and we saw something like example 6 already. We saw before tangent squared x, secant squared x. But if we recall, secant squared is the derivative, secant squared x derivative of tangent x. So if you say u equals tangent x, our du is going to be secant squared x dx. So this part is our du. So we have the integral of u to the 4th du. That becomes u to the 5th over 5 plus c, which is tangent to the 5th of x over 5 plus c. Pretty straightforward. And on to page 4. This is guidelines for making a change of variables. Let's choose a substitution, u equals g of x. Usually it is best to choose the inner part of a composite function, such as a quantity raised to a power, like a square root or something to the 5th power. Compute du equals g prime of x dx. Rewrite the integral in terms of the variable u. Find the resulting integral in terms of u. Excuse me. Replace u by g of x to obtain the antiderivative in terms of x. Check your answer by differentiating. I'm trusting you'll all be checking your answers. Theorem 4.14, the general power rule for integration. If you ever have some function to the n power times the derivative of that function, that's just going to be the function to the n plus 1 over n plus 1. It's just a restatement of this substitution when we have a power function. So u to the n du is u to the n plus 1 over n plus 1. And this should say plus c. And we can use that on example 7. And I'm going to try to not do a change of variable in this one. I know it's kind of ingrained in me to do the change of variable. Now, I have an x squared plus 1. If that's my inner function, its derivative is 2x. I don't have a 2x, I have an x. So I'll do this 1/2 times the integral of 2x times x squared plus 1 squared dx. So 2x dx, that is the du, so to speak. So this becomes 1/2 times x squared plus 1 cubed over 3. I'm sorry, this is limits of integration from -2 to 2. So we have 1/6 times 2 squared plus 1 cubed plus, or sorry, minus -2 squared plus 1 cubed. It's 1/6 times 2 squared is 4, 4 plus 1 is 5. So we have 5 cubed minus -2 squared is 4, 4 plus 1 is 5, so 5 cubed. And that's just 1/6 of 0, which is 0. All that work for a 0. Oh well. Let's go on down to 4.15. Change a variable for definite integrals. You can do these definite integrals using the change of variable with the u. If the function u equals g of x has a continuous derivative on the closed interval, a, b, and if f is continuous in the range of g, then the integral from a to b of f of g of x times g prime of x dx you could change it to, it should say g of a, integral from g of a to g of b of f of u du. Let's look at example 8 now. We're on the last page of these notes for this section. Okay, so if I say u is the stuff under the radical 2x plus 1, my du is going to be 2dx. I don't have a 2dx, so 1/2 du equals dx. And this can be changed to become the integral of 1 over the square root of u du. Now what's missing here? What's missing? What do you not see that should be here? If you're saying limits of integration, you're right. What about the limits of integration? It's no longer going from 0 to 4 because we did substitution. So if we do u of 0, we get 2 times 0 plus 1 is 1. And u of 4 is 2 times 4 plus 1, which is 9. So now it's going to go from 1 to 9. We had to change the limits because of the substitution. Now, you don't have to change the limits. You could write like u of 0 to u of 4, and then when you're done, substitute back for u, and then substitute back for x from u, and then evaluate it. Okay, this is integral from 1 to 9 of u to the negative 1/2 du. That's going to become u to the positive 1/2 over 1/2 from 1 to 9. So that's 2, because the 1/2 down below, times the square root of 9 minus the square root of 1. 2 times 3 minus 1. 2 times 2, which is 4. Oh, and I made a mistake, didn't I? Because this 1/2 du needs to be out front here. 1/2. 1/2 is going to cancel with that 1/2. Okay. So if you were screaming at the computer the whole time saying, Jeff, you forgot the 1/2. You're right, I forgot the 1/2, so that's gone, and it's just a 2. Okay. Sorry about that. Yeah, let's go ahead and look at this integration of even and odd functions. Hope you remember what even and odd functions are from your pre-calculus, even your algebra days. I teach this in my 096, what an even function is. Not this, because this is the calculus part. But okay, like x squared is an even function, x cubed is an odd, not just because of the power, because not all odd powers are going to be odd functions, but it has to do with symmetry with respect to the origin versus symmetry with respect to the y-axis. Okay, let f be integrable on the closed interval from negative a to a. If f is an even function, then the integral from negative a to a of f of x dx would be, and this is a very useful tool that I often forget to do, 2 times the integral from 0 to a of f of x dx. And if f is an odd function, then the integral from negative a to a of f of x dx would be 0. So example 9, evaluate the integral using the properties of even and odd functions. So we're talking about the integral from negative pi over 2 to pi over 2, so it's basically a negative a to a. Now sine is an odd function, because if you look at its graph, it's doing this type of thing. So it's symmetrical about the origin. Cosine is an even function, because it does this. Now, an odd function times an even function is an odd function, and that's the rule. That sounds kind of crazy, right? So if we have the integral from negative a to a of an odd function, we get 0. So this is 0. And that'll do it for 4.6. Oh, sorry, 4.5. I really hope you enjoyed that. Hope that meant something to you. So send me your questions. Thank you.